Okay, today's EndNote is by DK Panda from OSU.
Good afternoon. I know I'm standing between all of you at the dinner. We have a lot of material, exciting material I'd like to share. I think I've been here, out of the last 15, I think 14 years. I couldn't come to the first one, but I've been here every year coming and trying to share some of the latest and greatest things my group has been doing. So today I'll be focusing on high performance and scalable middleware for AI on heterogeneous clusters. So if you take a look, very broader look, what has happened over the years, like go back in 1975, this is where like a scientific computing, high performance computing started. Then in 25 years, like a big data came. So until that 25 years, people were working on all the high performance computing, then the big data analytics came, and people started looking at saying how we can take advantage of the HPC together with big data to make new findings. And in another 10 years, the AI world came, machine learning, deep learning, and that's what we have been living now. But then what is happening, there is a change is happening, okay? And that's what I'll be talking, and that is the right-hand side. So first, this is the left-hand side. I think many of us are familiar. In a centralized system, HPC cluster or cloud, we have the scientific computing, big data, and AI. But these days, what is happening is, I think you must have heard of computing continuum. So data is no longer centralized these days. You might have sensors, you might have all the different drones, data is coming from many different places, and you have to actually operate on this data as they are coming, whether it is the traditional HPC or big data or even the AI. And then you also need to see where you put the results, what to store, what not to store, so that in future you can actually reuse some of the data or the knowledge, okay? So that is the new direction. So to give you a feel, think of like a AI in digital agriculture, okay? Agriculture, as you know, is very important in all the countries. The traditional farmer might be knowing, saying, okay, I have some field, there are some diseases, I go and spray based on my old knowledge. Can I bring AI there? Instead of like trying to determine what exactly has happened in the field, you can actually fly a drone. And the drone, if it can carry actually an AI model there of that crop and the different kinds of diseases, then in real time, it can actually identify what kind of disease has happened. I'll actually show you. We have been working on some of these things towards the end. And then that information can either be passed to the farmer, or it can be even directly connected to the tractor. So the tractor can actually go and spray, okay? So if I can achieve that, then you will see that I can do very precise treatment of that farm, okay? So just think of like a precision medicine. Many of you must have heard of that field, has been going for so long. We can have actually precision digital agriculture, okay? So like this, there are a lot of situations are there. So the question is, can I bring AI to these common people, common scenarios, or societal challenges, okay? So in that case, we are actually democratizing AI. So that means AI is helping everybody, and that's what is also a big project I've been working on. And this is where you will see that computing continuum comes in. So the broad challenge is, how do we design this kind of high performance and scalable middleware while taking advantage of heterogeneous resources? So the resources remain the same. The CPU, GPU, all different GPUs, might be DPU, XPU, IPU, you name any XCPU. But we want to use all these things and try to come up with the middleware which will actually help us to achieve this, both the left-hand side as well as on the right-hand side in the previous figure I showed. So in that context also, I want to bring another dimension to it. As we are having like a HPC, deep learning, machine learning, and big data, so the question is, there are so many different software stacks, okay? Can we actually converge them to design a converged software stack? People have been talking about this for many years, but I'll try to show you that we actually have solutions. We have been working in the recent years. So everything actually fall back to MPI, and I'll try to show you why, okay? And once we have an MPI library for any kinds of CPU, GPU, DPU, IPU, you can actually not only run your traditional HPC, but you can also run your PyTorch, TensorFlow, Spark, Dask, everything will run over MPI. So you don't have to go and design each one of the stack for each of the systems in an independent manner, which is very expensive operation, okay? And so in that context, I'll try to focus, the talk will be divided into 4 parts. First, I'll start with the MPI MPI library project. Many of you must be familiar. If not, I'll try to introduce that. Then I'll go into the high-performance deep learning, both focusing on the training as well as inference. And this will be running on top of our MPI library, okay? You'll see how we have achieved that. Then the third one will be the high-performance big data and data science. That is the HighBD project. So here we have like a Spark and Dask actually running on top of the MPI, okay? And it is performance portable across all different interconnect, CPU, GPU, and all. And then finally, I'll talk about this. I'm leading a big $20 million NSF AI institute. In US, National Science Foundation has invested on 25 such institutes. So if you do a quick math, 25 million times 20, $500 million. National Science Foundation has invested, so we are one of those. And our objective here has been to really design the cyber infrastructure for that computing continuum, and I'll show you some overview of that institute. So let's start with the MPI library. As many of you must be knowing in this community, we have in here almost the day 1 of InfiniBand. When InfiniBand came, prior to that in my group, we were working on MiriNet and Quadrix. How many of you remember those interconnects? Some of you, right? That generation is reducing. So we are working there, and when InfiniBand came on October 2000, in my group, we were the very first one to be ready, saying how to use InfiniBand for HPC. And we had the first open source MPI called MPI, and we demonstrated it at 2002 supercomputing conference, okay, in Baltimore. And that was the first time people actually saw an MPI running over InfiniBand cluster. And it was only 8 nodes. And I still remember those days, 8 nodes were not stable enough. During the demos and all those things, it used to frequently crash. But now you can see 8,000s. 10,000 nodes are being deployed, and that's what has happened in the last 24 years. I'm very proud of my team, so we have been in that ecosystem, helping with that community. And that MPI project is strongly growing. As you can see, we are hitting to very closely like a 4,000 organizations, 3,400 organizations in 91 countries. Just from our website, we have crossed so far like a 1.77 million downloads, just from our website. The library is also part of the Red Hat, SUSE, Spark, OpenHPC. We don't keep track of those, as well as some of the vendor libraries and all. And that has been enabling a lot of top 500 clusters, so we have been enabling this community over the years. So this is a very high-level overview of the software. Below here, we have all the different networking technologies. Here, we have all the different accelerators, including DPU. This is where actually in between, we have the APIs and mechanisms, our communication runtime, and this is where we carry the research. As you would have been seeing, we always first come up with the designs, publish those, and in 6 to 9 months, we actually take that into our MPI library releases. So within my group, we have a lot of full-time staff people. We have almost like 200 servers running continuous QA. Okay, so all those designs we translate into 6 to 9 months and then push it out. So over the years, like we started with MPI, then we moved to PGAS, so that was the layer we had worked on. But now recently, in the last several years, we are actually linking that to not only the HPC, but the deep learning, machine learning, and big data and data science. So that's how we are able to design this converged software stack, and I'll go into a little bit of more details in the later slides. So this is our very latest release. If you have not seen, that is the 3.0 version. So what we have done here, earlier we had the verse level design, which was working on the InfiniBand and Rocky, then we had the Omnipath, PSM, and all. But now, many of you know this networking community has been divided into two clubs. One is the UCX club, other one is OFI club. Okay, I call them club. I mean, they have their own features and all those things. So now, in this latest release, we are supporting both the clouds. Okay? So through that, actually, MPI can now run on any interconnect. Okay? Earlier, we were not able to run on, let's say, Slingshot and all, but now we can run. Okay? Because Slingshot is being exposed through OA5, and we have supported the OA5, so we can actually run MPI on all the Slingshot-based systems. In addition to InfiniBand, Omnipath, Rocky, iWarp, you name any interconnects, we support those. So here I'm just some sample numbers. You don't have to take a look. We always try to deliver compared to like MPI's 2.3 series. So this is the new 3 series, 3.0 series, so we are able to deliver better performance. Now, I also want to introduce, some of you must have heard of the previous, some of the talks, this CUDA-aware MPI. How many of you have heard of that term? Some of you, okay. So once again, we introduced that as a joint project between OSU, Mellanox, the previous incarnation of NVIDIA's high-performance networking, and NVIDIA. So that time, like a 3-party work we did to bring this CUDA-aware MPI. It was in 2011, we published the first paper at ISC conference, and for last 13 years, people have been adopting that idea. So the broad idea is that if I have like a right-hand side, we have this is the GPU and InfiniBand. Instead of like taking the data, doing a CUDA mem copy, then doing MPI send, MPI receives, and then the other side we do receive, I can actually call this MPI send from the GPU buffers on the receive or the sender side, and MPI receive on the receive side. And then let the MPI library figure it out. Okay? And that will actually reduce the communication overhead and then really give the performance. Okay? And that leads to this high performance and high productivity. And a lot of other MPI libraries, even the collective library like Nico, there's a lot of storage, file systems, everybody is using that CUDA-aware MPI. But recently, for the last 3 years, we have brought out a new concept. And I'll try to show you that on-the-fly compression. So the idea is that if I'm sending a lot of data, and especially these days, if you see like a lot of systems are coming with 4 GPUs, 8 GPUs, connected with NVLinks, but once you are trying to go out, you don't have enough bandwidth. Then depending on the data, can I actually do on-the-fly compression on the sender using GPU? Okay, because compression using CPU is not very efficient, but GPU, when I'm trying to, before I communicate, I actually compress, and my data reduces, depending on the factor of the data, your application, and especially I'll try to show you later on, it is good for AI. Okay, because AI, there is a lot of sparsity. All these data we are continuously sending, you can actually compress very nicely. So your data size reduces, and your bandwidth increases, latency reduces. Okay, so you get a boost in the performance. So this we started like 3 years back, as I said, May 2021, IPDPS, we had this one was the best paper finalist. So first we started with scientific computing. So this is an AWP ODC. If some of you know, this is a scientific simulation of earthquake in California. It's a production quality code. So in that code, we were able to show that if you do this on-the-fly compression with using like a different compression algorithms like MPC, GFP, you can actually boost the performance. The left-hand side is like a flops, higher is better, and the right-hand side is the runtime for time step, lower is better. Okay? So it's the same hardware. We are not changing any hardware, but using this on-the-fly compression, we can actually boost the performance from 20% to 35%. Okay? And by the way, these are all parts of our release. Anybody can just download, and you can actually try to use all these things. So now what we have started doing it, the motivation I said, like the converged software stack. So let's say our MPI library supports all the CPUs, GPUs, DPUs, interconnects. Now, in addition to the HPC, can we actually provide support for all this AI workload? Okay? Like if you're running on TensorFlow or PyTorch or distributed PyTorch, instead of trying to go and optimize to the lowest network, you just link to our MPI library. And since our MPI library is optimized for all those networks, you immediately get the boost in performance. Okay? Now, if I do the same thing, actually you can do for the big data and data science. Now, in this cluster world, if you take a quick look, the complexity is actually growing. Okay? The commodity cluster computing, I know so many of you are vendors here. Let's just take a CPUs. Broadly, I can say like 3 categories of CPU. x86, and then AMD and Intel, and then the ARM. Okay, so there are 3. GPUs, there are 3, NVIDIA, AMD, and Intel. So 3 times 3, 9 combinations of clusters are already there. So then bring the interconnects. Might be another 3. Okay, Slingshot, InfiniBand, Rocky. There are, of course, Omnipath and all those things are there. Or if I do that 4, so you do 3 times 3 times 4. 36 different cluster configurations. Okay? Now, for an MPI library, of course, there is a big challenge in optimizing all these different combinations, and we have been trying to do that. But now you think of not just the MPI library, but somebody has to optimize that AI workload on all those 36 different configurations, or your Spark workload, or Dask workload. That is lots of overhead. So we can cut down all those overheads, saying if an MPI library for us or any other, you name any other library, MPI library, if they can actually optimize, because MPI library is always the first one. Any type technology comes, MPI people jump in and try to deliver you the good performance and scalability. So why not leverage that? And not only the complexity reduces, but a lot of modern workflows, if you will see, they are actually combining many of these things. I think yesterday we heard some talk, like AI is being combined while the HPC simulation is running. Or the big data analytics Thomas indicated yesterday, like you are trying to combine that with AI and HPC. So all those complicated workflows, you don't need like 10 different software stacks. Like I do some steps, push the data into my storage, then again bring it in, and again compute. You don't have to do all those things. Okay, so this will help you achieve that direction, and that's what for the last 2-3 years we are actually trying to go for. And that is our MHAPIS Plus. That is the new release. So we have the base version MHAPIS, then we call it MHAPIS Plus. And this is where, again, it supports all the different interconnect, as I indicated. And this is where we have all this optimized design. I'll go into some of these things. We have an MPI4DL, MPI4QML, MPI for Spark, MPI for Dask. Okay? So as long as you have all those modules, and these are all released from our website, you should be able to actually go and build all these things for your systems. So these are, again, some sample numbers I'm just trying to show. I'll not go into detail. So these are like NVIDIA plus IB combination, NVIDIA GPU and InfiniBand. We give good performance. This is like a AMD GPU plus Slingshot. Okay, I'm just taking some sample numbers. MHAPIS Plus runs on all these platforms. These are some initial numbers for the Intel GPUs. As many of you know, they're just coming. You have not like a very large-scale accesses yet. But these are some initial numbers based on the access we got. This is a kernel-less network, Omnipath plus Intel GPUs. And here you can see that we are able to even beat Intel MPI. Their own designs, we are able to, MHAPIS is able to give better performance. These are the latency intra-node, 4 GPUs. And this is like a collective all-to-all. Left hand is the latency. You can see MHAPIS Plus for large messages is able to give very good performance. And in fact, we have running also this an FFT, which is an application, high-performance FFT application. The higher is better. You can see the MHAPIS Plus is able to push the performance significantly better than Intel MPI. This version has not been released. It will be released soon. So then, of course, the DPU has been there. So we are also working on the DPU, especially the Bluefield 2 and the Bluefield 3. And so if you take a look at this, this architecture, in the Bluefield, we have like these are the hosts. These are the ARM cores on the DPU. I call it like an executive assistant paradigm or executive secretary paradigm. Okay? So how many of you here have assistants? How many of you have assistants? Or secretaries, whatever you can say. I'm sure many of you are managers here, am I right? You have assistants? Okay. So the question is, if you have like a PhD degree holder assistant, what can you offload? Everything. You tell your assistant, go and submit a proposal, get the research funding, write the paper, do the design, put the report, just add my name. Right? That's what you do. But getting a PhD level assistant is very expensive. Okay? So typically the assistants don't have that much, unless you have, I mean, sometimes the CEOs have like a PhD level assistant, right? But in common cases, you have like a assistants who have like some kind of a degrees, college level. So depending on the qualification of those assistants, you need to see how much you can offload. That is the first thing. And the second thing is that once you have an assistant, you need to rethink about your workflow. So let's say I didn't have any assistant. Tomorrow, my boss is saying, okay, you're doing very well. I'll give you an assistant. But in that case, I need to rethink. What should I do and what should I offload to my assistant? If I continue to do everything myself, and that assistant will sit idle. Okay? So that means my workflow has to be changed. Okay? So that's what is happening with this DPU technology. You say DPU, IPU, or any XPU. You have to first determine how much you can offload, and then you have to change the workflow, or in this case, application. You have to change. Unless you do both, you will not see the benefit. Okay? And that's what we have been working here. This is being jointly done with a startup company called Xscale Solution. We have a package called MPI4DL. We started with non-blocking collectives. Many of you must be knowing non-blocking collectives were introduced in the MPI 3.1 onward, saying that if I want to do an all-to-all or all-reduce or scatter-gather, I can initiate that operation, and while that operation is happening in the behind, I can actually compute my compute can progress. So it's exactly executive secretary paradigm. That means for your secretary, you just tell him or her saying, okay, do this, and while the secretary is working on, you try to do your own work. So then the thing is, the overall metric you need to measure is not how much time the secretary is spending or how much time I'm spending. What is the overall time is being taken for that workflow? Okay? And that's what we did here. So this is an OSU I all-to-all. So here what we are measuring is compute plus communication, and this is a part of actually OSU micro benchmark suite. Many of you must be using that. That is also from my group. We have been doing that for the last 24 years. So using that numbers here, you will see this is on the Bluefield 2. For very large messages, we are able to cut down the overhead. Like the red bars are MPI2, and then the green are MPI2DPU. We are able to give very good benefits when we are able to offload. That is just for the all-to-all. But then the second thing you remember, I said the workflow has to be changed. So in this case, your application has to be modified. So you worked with, in this case, P3D FFT, those people from SDSC. We actually changed. They were using blocking all-to-all, and we worked with them to modify that algorithm, saying, yeah, you can, let's say you compute a little bit and then do all-to-all, but while all-to-all is going on, you also do additional computation, okay, so that we can overlap computation with communication. And if you can do that at an application level, in this case, we are able to give you 24% benefit, okay? And these are numbers on, I think it is 1,000 process runs on 32 nodes with 32 ppn, and all these different grid sizes. That's the kind of benefit you can see, okay? So that is for the all-to-all. So similar things we have done for broadcast. And broadcast is also very commonly used in HPL, high performance lean pack, many of you are familiar with. And this is a CPU-based HPL, so we also modified HPL, okay? So we have an Xscale HPL DPU, and then here you can see, even in the, with a modified version and then offloading the vcast, we can give you like a 15%, 17%, depending on what problem size you are running. And those of you who do HPL benchmarking, you'll see 5%, 10% is not a small number for HPL overall performance, okay? So then same thing we have done for other collectives we have been doing. It is an I all-to-all V, which is a vector version of I all-to-all. Similar kind of things you can see starting from different message sizes, 64 ppn, 128 ppn. We can give you 72% benefit. And then we have used this on a code which is based in UK. I think some of you know this XCompact 3D code. So we have actually modified that to take advantage of this DPU offload. So there again, we can see like this is on 8 times 128, 1,000 process runs, we can give you 10% boost in the application level performance, okay? So then gradually, so those are all the non-blocking collectives. So now in some of the recent releases, we have started working on point-to-point. As you know, the MPI has MPI send, MPI receives. Those are the non-blocking point-to-point. So that also we can offload, especially the rendezvous steps. And this is a 3D stencil benchmark. So here you can see like a 13%, 18% benefits you see with the MPI2DPU. And then recently we have taken that to PETC. I think yesterday we heard like some of the talks, people were using PETC. So PETC is a very common toolkit, and a lot of other libraries, like here you will see AddFlow, DFOam, Moose, OpenFOAM, a lot of them use PETC. So if I can boost the performance of PETC, then I can actually see benefits in a lot of other applications. And that's what we have done here. These are the latest with the Bluefield 3. And this is like a 256 by 256 by 256. Here I see like up to an 8 node. This is a 32 ppm, so 256 core runs, we can give you like an 18% benefits in the PETC by using this executive secretary paradigm on the DPU. Okay? So we are continuing along this direction, and you will see more releases coming out here. So if you are having any DPU cluster, you should be able to actually download our stack and then see whether for your application you can get these benefits or not. Okay? So these are some of the HPC sides. So let me move into this machine learning and deep learning. So here the thing what I want to indicate, so again, there are multiple of these components are here, and these are the different components I'll try to focus on, just give some high-level perspectives. Now, one thing I'd like to say, just like the HPC, traditional HPC has been there. People have been optimizing, let's say if you have an OpenFOAM, okay, or let's say GROMACS, or you name any VAS, for any of these applications, as the system sizes are increasing, new technologies are coming, people are continuously looking where to optimize, what best scheduling I do, where to distribute the jobs, how to reduce the communication. That has not happened yet for the AI world. Okay? That's why you hear about, oh, training takes like 5 months, 6 months, inference takes so much time, it is for every query, it takes 25 cents and all. Because all these ideas came from the AI world, and those people are not experienced with HPC. Okay? In fact, this is where I think not only in my group, a lot of other groups have started jumping in. I'll try to show you some of the initial numbers where you can actually go inside. So think of this LLM training is like your application, like an HPC application. You can characterize what is happening in the application, whether my jobs are being placed properly. If not, I can have better job placement. I can have a better scheduling. And each one of these will actually help you to get better and better performance. And that's what we have been doing here. So I'll start with the very first, how we have linked that to the MPI-driven high-performance distributed training. I'll talk about data parallelism, model parallelism, on-the-fly compression. And then we have come up with this mixed-and-match communication runtime. Then I'll give some examples of like accelerating parallel inferencing itself, in-flight batching with the mixed-servo export models, high-resolution images with quantization, then how you can actually also have hyperparameter optimization and fine-tuning, how do you accelerate QML applications, and then again, how you can take advantage of these DPUs for even your training. Okay, so I'll try to go over all these things. Please note that each slide is like a paper. I'll just remain at a high level. I'll share the slides. You can take a look at it in more details. So first, what we have done, so this is where I was telling if, how many of you know internals of like a deep speed, torch distributed PyTorch? How many of you know? Internal, okay, some of you, okay. So this is where, if you take a look at it, started with Horoward. So when Horoward came into the picture, that was the middleware. So they actually provided 2 different APIs you can think of. You can link to, like most of this training, all reduce was the most common. Nowadays, of course, all to all, reduce scatter, and all those things are also people are using for training. And these are collective operations. And especially if you take a look at the MPI community has been optimizing these collectives for 30 years. Okay? For some AI people, it looked very sexy. I'll just put it in a very joking manner, saying, oh, I can use all-to-all. Okay? But all-to-all is nothing new. I mean, it has been there in the MPI world. So Horoward actually, first one was trying to provide an API, saying, OK, I can link this to MPI. Okay? And same thing is PyTorch distributed is doing. So what we have done, here actually we have taken that path, and we have linked it to our MHAPISTO library for appropriate CPU training, CPU-based training, or GPU-based training, or DPU-based training. Okay? Of course, different vendors have different solutions. Nickel, Rickel, all XCCL libraries are coming from different vendors, and they are reinventing the wheel. Okay? Whatever has been done in API, they are trying to go and trying to optimize. So MPI library already has those things. So through this actually, So with this, so we have a library here. So this is what we call MPI-DL. You can actually go and we give you the recipe kind of thing, saying how you will modify, how you will install, all these things. So the end user doesn't have to worry about anything. The end user still runs things with PyTorch distributed. He or she will not see any difference. It is the system which is running on top of MPI. So here I'm trying to show this, like these are some of the runs on Summit. You remember like the Oak Ridge Summit, which used to be #1 system a few years back. It scales. MPI scales here like a 1536 GPUs. Same thing, you can actually do CPU-based training. Okay? In fact, I know there is a lot of people say, oh, training has to be done on GPU. It doesn't have to be. I mean, if you have large CPU cluster access, you can actually try to use the CPU resources also. So here we can show this is running on the TAC on 2,000 nodes. And here you see like it delivers up to 260 images per second. And you can actually train like a ResNet 15 7 minutes. Okay? So then those are like the data parallelism. And as you know, the model parallelism has come next, because data parallelism, depending on your GPU memory, if your model is very large, you cannot use GPU data parallelism. So you have to go to model parallelism. But then the model parallelism brings additional synchronization, additional communication overhead. So we have optimized that. And this one is running on, let's say, I think 1,000 V100 GPUs on the Livermore Lassen system. And here you can see we have got like almost 97% efficiency. So here let me bring back that on-the-fly compression I talked earlier. Okay? So that is our first initial paper on the point-to-point on-the-fly. So now we have started taking that on-the-fly concept to all the collectives. Okay? So this is an all-to-all online compression. This we presented at ISC 2022. So the left-hand side is like a PSDNS. That is a traditional scientific simulation. We can accelerate by here, if you see, like a 29%. The right-hand side is actually deep speed. So some of you know the deep speed is the middleware, and that actually underlying it is just all-to-all. And if it is using all-to-all, I can actually provide my on-the-fly compression, and then you see I can get a boost 35% there. So then recently what we have done is, so this is a paper we just got accepted to be presented at ISC, I think in next month. So now we have started doing all reduce. And as I said earlier, a lot of this training use all reduce. So now if you use the on-the-fly compression with all reduce, so these are the numbers with this is a very dense slide. But look at these numbers, like I can reduce the training time per epoch by 32%, 26% kind of things. Again, the same hardware. I'm not changing anything, just the software innovations. We are able to give better and better performance. So then we have gone into more details. This is how you can take like a LLM training. We have analyzed the different paths, and we have come up with a hybrid compression. The same compression may not work in all the different stages of your training. Okay? And so here what we have done, like a hybrid lossy compression, for a throughput-oriented training, MG hybrid for a both throughput and accuracy-oriented. So this has been again accepted to be presented at CC Grid next month. And here if you see that hybrid compression results, so these are all the details I'm providing here. I'll not go into all the details like this, the different kinds of parallelism and 0-1 we are running here, and then I can give you like a 17% boost in the LLM training time. Okay? So this is what I was telling. Like people have not actually understood all the communication patterns. The more people can understand these LLM trainings, how it is happening on the modern systems, and we can actually, the HPC world can provide solutions so that you don't have to, like these trainings will take quite a long time. So then this is a nice thing we have done called a mix-and-match runtime. So earlier I indicated like MPI has all these collectives. Similarly, all these vendors are also providing their own collectives, the Nickel, Rickel, XCCL kind of things. Now, depending on the training and what like a middleware you are using, like a deep speed or distributed PyTorch, might be, as I said earlier, it is using, let's say, deep speed is using all-to-all. But the question is MPI library optimized for all-to-all for 2 megabyte messages, or Nickel is optimized for 2 megabyte messages? Okay? So these are like, as you know, over a period of time, all these libraries are being optimized. So might be Nickel has optimized all-to-all for 4 gigabyte, but not for 2 megabyte. Whereas MPI library has optimized for 2 megabytes, may not be for 8 megabytes. Okay? And also the PPN. So all this tuning depends on like your PPNs, your message sizes, your system sizes. So we provided a mix and match runtime. Okay? So on the same system, you might have Nickel installed, you might have MPI installed. You try to do, we provide a recipe. Here we call it like MCL-DL. So which will do very quick analysis of the tuning tables. Okay? Run some few experiments, and then see which one is better and how to mix and match, as the name suggests. And then if you use that, you see, you can actually get a benefit. Here we have like a 1.5 times, 1.4 times kind of things. You can get the benefit. Okay? So that we are allowing the end users to take advantage of. So those are the training. Let me move to the inference. So this is again the inferencing. As many of you know, how many of you actually queried ChatGPT? Many of you, right? So once you initiate, you will see there is a light blink, 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 blink will be coming, right? Until your response comes back. So that is the time your request is actually going to that server, it is getting scheduled, and then coming back, your response. Okay, so think of it like a client server. So the inferencing is running somewhere, and you are seeing this round trip kind of things, in addition to how much time it takes the inference. So think of like job scheduling. Okay, the old HPC world, many of you would have seen job scheduling. Okay, so you have a bunch of servers, the new job comes, where do you put it? How do you put it? It's very similar. Okay, so what we try to do, we went actually internally, looked at those code. Some solutions are there like dynamic batching, concurrent instances. We propose something called a proposed temporal fusion. And with that, I'll show you the next slides. We get a very big boost in the performance. We just presented in the HiPC conference in December. And we have actually made a release. We call it like a parallel inference release. You can go to our IDL. And here, if you see, compared to fast transformer, our method actually can improve by 16x speed up. Okay? Then actually what happened, as soon as this paper got published, we got some queries from NVIDIA saying, oh, what your guys are doing, we have not done this. Then we discussed, then they have taken the design into the NVIDIA's solution thing. So think like this. Once you understand all these communication patterns, you should be able to actually achieve better and better solutions. So the next thing is, this is another paper recently, just got accepted. Many of you must be knowing all these things. In the inference, we have mixture of experts. And if you try to see these inference or the models, there are multiple layers. So there is a lot of affinity. We try to analyze, like this is the heat map between how much affinity exists between those mixture of experts, between layer 0, layer 1, layer 3, layer 4, like this. So then the question is, where do I run it? If I have a cluster of GPUs, as many of you know in the HPC, those who are in the near affinity, those who are talking more, if they are in the nearby GPUs, your communication cost will reduce. But if they are scheduled far apart, then the communication will increase. And that's what we have done. This will be presented at IPDPS conference. Again, I don't want to go into more details, but here we were able to show that if you do this good kind of a affinity-based scheduling, your LLM inference performance can be improved by 200%. Okay? So all these are HPC techniques. Okay? So the question is like, we need to bring those HPC techniques to the AI world so that all these AI workloads actually can run faster. So then, of course, inferencing, again, is related to quantization. As many of you know, you have a model, but then if you want to run it on a drone, or you want to run on some sensors, or even a small laptop at a remote place, you may not have enough memory. So you have to work on this quantization, and that's what we have done. This will, again, we just got accepted into a PERC paper. So here we have shown, like using, compared to FP32, if I go into int8, then we can have actually a 5x memory reduction, 6x speed up, and similar kind of things with also have precision. So those are the kind of the things, training and inferencing. And then, of course, there is a lot of hyperparameter optimizations. And this is where, again, a lot of cycles are going. People are continuously trying to have these parameter optimizations to. So here what we have done is like we have introduced a new framework called HyperSAC. And this integrates, again, advanced scheduling schemes to increase the utilization of the GPU architecture. If you take like A100 or H100, you can actually reduce and this optimization time by a factor of 4, as shown here. And then, of course, very recently, people have started talking about fine-tuning. You have the larger model, and then after that, you do fine-tuning. Then how do you do those fine-tuning? So here, there's an approach here. This is an ongoing work. I'm just showing some initial results. Like we call it parameter-efficient fine-tuning. And then we try to freeze most of the model weights and update only a small fraction. So we are not updating all the weights, and updating all the weights is more time-consuming and requires more memory. But if I only identify like which are the more critical ones, and then we focus on those, then we can actually speed up this fine-tuning also. So then moving ahead, those are all the deep learning. We have done similar things for machine learning, the traditional machine learning. So here again, for the machine learning, some of you might be familiar, like there's a package called QML, and that traditionally has been running over Nickel, which is the NVIDIA's solution. What we did is we actually linked it with our MPI-2 GDR, which is our CUDA-aware MPI. And here, if you take a look at some of these things, k-means, linear regression, nearest neighbor, truncated SVD, et cetera, you can see the benefits compared to the Nickel. Like I can give you 1.6x, 1.38x kind of benefits. Because we are trying to optimize our MPI libraries, the collective operations to get better performance here. And again, this is a released. You can download the QML, install it on our GPU cluster, and you will be seeing the performance. So then the same things we are trying to do in the DPU-based. I showed you earlier the HPC results. So the question is, can I also take advantage of DPU for DNN training? So here again, this is the work jointly done with the Xscale solution. There is a package called Xscale AI DPU. And here, in the training, there are multiple steps. So the question, again, you need to see, based on my example I gave earlier, like a manager versus assistant or executive versus assistant, what executive will do, what assistant will do. So we have done a appropriate work division because assistants are not very fast. So you need to keep that in mind. And if you do that, then we are able to get like a year around 20% improvement on the training. And then similar things also here we have done, like a checkpointing. I think yesterday we heard about that, like the training. There's a lot of time is going on checkpointing. So how you can offload that? So here you can actually offload to the DPUs. Because DPUs are assistant, they're actually good for these kind of activities. And then if you do that, then you see the improvement goes up to like here up to 30 nodes, we are seeing around 35% benefit. So that's how actually we are bringing the AI world to run over MPI. Okay, remember I motivated that converge software stack, and this is what all you can do. So now let me quickly go into the HighBD, which is the big data, and then I'll go into this high-school project. So here again, what we have done is to bring that converged software stack. Now Spark can actually run over MPI. Dask can also run over MPI. So this is what in my group earlier, in fact, here also I had presented, we had a project called HighBD, High Performance Big Data. So we took actually Hadoop, Spark, Memcached, all these things, we went into the InfiniBand verse layer. That was very customized design. But doing that for every interconnect is just a waste of time. So this is where, again, I motivated. If I can link it to the MPI, I get the benefit. So that's what we have done here. So if some of you are familiar with the Spark architecture, so we took the native transport and client and linked to the Java bindings to the native MPI communication library. And now you can see, here I'll try to show you. So these are running on TAC Frontera, which is an InfiniBand system. This is on TAC Stampede 2, which is the Omnipath. We didn't do anything for Omnipath. It just ran. Because it's running over MPI, MPI can satisfy, or MPI can run over Omnipath or InfiniBand. So we are able to get a good performance around like a 1.4x, 1.5x type thing. So same thing we have done for Dask. Those of you who are familiar with Dask, I think there was yesterday some talk on that, I believe. So Dask is currently running from NVIDIA side. It's only running on the UCX. So here again, we introduced this MPI Dask, MPI for Pi, linked it with our MPI-2 library, so we can take advantage of that. And here, if you see, this is on a TAC Frontera GPU subsystem. It's like a 2.9x compared to UCX. Of course, compared to IP over IP, we'll see a lot of performance, but we are able to give good benefits compared to UCX. And here on the right-hand side, similar kind of things. This is the throughput. Higher is better. We can give you like a 2.9. So these are, again, the releases. If you go to the HighBD side, you will see MPI for Dask, MPI for Spark. You can download, and if you have any applications, and Dask has our support, both CPU as well as GPU. And then you should be able to run these things. So with all these things, let me move to the final one, which is, I mentioned that computing continuum, okay? And also to democratize AI. So I'll talk about these two. So these are all the so far like the left-hand side. So now let's move to this right-hand side. I gave that digital AI in digital agriculture example. How we can actually design this kind of a system, okay? So this is the NSF AI Institute. It's called iCycle. You can actually do a QR code or just go to iCycle.ai. You will find out a lot of details. It is one of those 25 AI institutes funded by National Science Foundation. And so the idea is that if I have this kind of a computing continuum, and we have taken actually, I talked about digital agriculture. We also have 2 additional use cases, use science cases. One is smart food sets. So what means the food logistics? So all of a sudden, let's say you have some emergencies, like a freeway, especially in California, you know, some heavy rain happens, some highway is damaged, or let's say some fire comes, or some tornado is coming. All of a sudden, you see disruption. So how quickly you can move the logistics around, okay? And that too also, we want to give the control to even a truck driver, even to a shop manager. They can take decision, okay? So that's what we are trying to democratize. So we are trying to build those kind of environments where they can actually see, interact, and that through with a conversational AI, okay? Like just a farmer can ask, the farmer example I said earlier, farmer wants to harvest, the farmer can ask, just like an app, saying, okay, should I harvest today? Behind the scene, it will actually go and see what is the market condition, what is the transportation available. It'll do a lot of analysis and see, okay, if I can delay the harvest by 1 day, might be the farmer may make more money, okay? So it will give that suggestion. So all these things we want to convert into like an app, which is like an iPhone, so that the end users can actually talk. So that is the whole idea. So here we are talking, so this is the entire iCycle stack, and it is a very large organization. I am the overall PI, but there are 150 people working. There are 14 universities. There are, as you can see, like 33 faculty, 41 staff, almost a 150 members team working here. So the idea is to design this kind of software, and later on I'll say we have already started releasing a lot of these softwares. And anybody can actually take those and start building these different systems. We have also extended, it has gone global. We got a joint funding between US and also India, okay? Because agriculture, as you know, I mean, it's important in all countries, okay? And recently we are trying to set up something with Australia also. I was at SC Asia, I think 2 months back, 2 months back, so they had the talk, so they want to establish some collaboration. So like this, I think we have talked to some of the UK people here. Very similar needs are there in all countries, okay? And those softwares, the question is if I can design those kind of software, how people can try to utilize this. So this is our overall vision. Inside this system, everything, there is a lot of components, foundational system AI, cyber infrastructure for AI, AI for cyber infrastructure, software, explainability, privacy, accountability, data integrity, co-design. But the end goal is to do very simple conversational AI. So I'll not have time to go into a lot of details. I'll just try to show a few components. This is like a foundational systems AI. So within foundational systems, these are the different thrusts. Like how do you create knowledge graphs, okay? You have all these like different kinds of distributors. Let's say the logistics I said, different companies, different trucks. How do you bring all those things? Traditionally, they have been done database. But based on database, you cannot run training and inferencing and all. So all of those need to be converted into large-scale knowledge graphs. And then on top of those knowledge graphs, we can actually run these things. Model commons, similarly, like we have to put all those different models in a model commons. I gave an example of like this drone flying. So there are so many different types of drones. And depending on the battery life of the drone, and the amount of memory, can it actually select an appropriate model for a given crop? Can it have that kind of an intelligence? Okay? And that's what we are trying to build model commons. Similarly, we want to do a lot of adaptive AI. That means if, let's say, the drone is flying, there is not enough bandwidth to the base station or to the cloud, can it take a lot of decision? Okay? What data to store? Can it change to like a inferencing, as I said, in different kinds of quantization levels? So all those things we want to automate. Okay? But before automation, you need characterization. You need modeling. Okay? That is the part of the research, and then it will get converted into software. Then, of course, federated learning. That is very important for all these privacy, accountability, data integrity kind of things. And, of course, there is a very big focus in our institute about all these LLMs because we want to do conversational AI. Of course, conversational AI, LLMs, if you take it to agriculture, that is very different than what you do with ChatGPT. And that with the digital agriculture, what you do in India, the LLM version will be very different than what you do in the US or in Argentina or in any other countries. So this all needs to be fine-tuned, okay? So, and customized for that kind of a domain. So then the thing is the CI for AI, that is cyber infrastructure for AI. Of course, the big component is high-performance training. I talked about that, high-performance data management. There is edge intelligence. So like this, out of those 150 members, different teams are working on all these different research agenda, and then we are trying to put together all these things. And this is actually our co-design. And actually in our team, we have actually a lot of non-computer scientists, like animal ecologist, faculty from School of Food, Agriculture, Dairy Distributions, okay? So we are working with them saying, okay, how AI can actually help them. So they bring problems to us. We are trying to provide the solutions, and then we are working together to have this end solution. So I'll just take one such example, the digital agriculture, so that you can get a feel for that. So I motivated this example like a crop, how dynamically I can detect, like a drone flying, identifying the crop health, informing the farmer, or even in the end, you want to connect it with the tractor, okay? So we want to totally automate, and this is where all the steps are there. How do I do data harvest, preparation, HPC, how do I use HPC to the field? So I'll just take a few little steps. There are a lot of these challenges here, application domain, data labeling, how do you do training, how do you do quantization, and how do you do aerial crop scouting, and then you need to put everything together. And that's what we want to provide, like an AI as a service, or a digital agriculture as a service. So start with this. So think of here, it's like just take like a 1 or 2 crops, like a wheat or corn. These are all the different, like what is happening on the soil? What is happening, let's say wheat, how is it growing? Is there a non-uniform emergence? Is there a different kinds of pesticides affecting? All these things are vision problems. Can I come up with models first? So that is the big challenge. If I have a lot of images, from these images, can I actually say that, look, there is a corn borer is happening. European corn borer has affected this cornfield. Okay, we want to do it automatically. Okay, and now you can think of like so many thousands of these crops. Okay, it requires huge kind of analysis, and then of course you cannot do a full-fledged learning here. That is impossible. Okay, if you get like millions of these images, so here we are trying to do something called a semi-supervised learning. Okay, so we have designed this thing called harvest. So we call it like this harvest can actually run. This is a software, think of like a semi-supervised learning software which can run on an HPC system or in a cloud. Okay, and then what we say is like bring your own data. Instead of bring your own beer, we say, okay, bring your own data. And it will actually give you that interface. It will do the training, go through all these things, and then you can actually get your model back. And you can download that model and take it, use it. If you want to contribute back the model to your model repository, you are also welcome, so that others can start using it. So that is the kind of the democratized model we are going through. So here what we did is like let's say soybean and crops. We got like 1,000 samples, but training 1,000 samples itself with different classes were very expensive. We used the semi-supervised learning on just only 80 samples. Okay, out of those 1,000, just using 80, we are able to improve, we got like a 97% accuracy, 93% accuracy. And of course, these kind of, like the agricultural people were just running on a single GPU. Of course, we converted that into multiple GPUs. We improved the execution time. So then, to automate that process, this is where we have been doing a very thorough analysis of all capabilities of edge devices. So like you can have all these different softwares are running, the OpenVINO, PyTorch, TF-Lite, Onyx. We are trying to do a very thorough characterization because dynamically we want to detect what model to run, how much memory will it take, how much battery power is good enough for the drone to run these kind of models. And in the end, so this is already we have, this is my colleague, Professor Chris Stewart. So think of like this is, we are working with a firm in Ohio. You can actually fly these drones. And sometimes for very large firms, a single drone may not be sufficient because drones, have some battery life, like a half an hour or 1 hour. So we are trying to put parallel drones. We can fly 10 drones, and they can actually communicate. So we are taking parallel processing to the real edges, to the drone. And then in the end, based on those models I indicated earlier, they can actually give you this heat map. Okay, this is a 2-color heat map. It says red means some disease has happened there, which we are trying to detect, or it could be multicolored. Okay, so saying, oh, this part of the field has disease 1, that part of the field has disease 2, or that part has both disease 1 and disease 2. All those things we can do real time. Okay, and that is the goal, and if we can achieve that, then we feed that to the tractors. Okay, so you can think of like a first drone start flying, after 10 minutes or 5 minutes, the tractor starts flying. Oh, sorry, the tractor starts driving. So the information is coming in real time, and this tractor will go and then actually spray the appropriate pesticides in a very precise manner. So that is like the precision digital agriculture I talked about. Okay? So that is the kind of the systems we are trying to achieve. And here, many of these things, the components have started being released. You go here from the software download page. Every 3 months, we are releasing some of these components in all these different domains. We are on the 3rd year of this institute, 2 more years to go. In the end, we'll be not only be giving all these components, but we'll also be giving the end solution. Okay? So that is the kind of the idea. So there are a lot of collaboration opportunities here, engagement. I just want to highlight here, not only from different institutes, as well as like industry. We have industry partnerships, stakeholder roundtable. Any one of you are interested, please feel free to talk to me. So with this, let me conclude here. As I indicated in the motivation, as we move into this post-exascale system and cloud, we need to take a holistic view of HPC, AI, big data, data science, everything. We need to end this computing continuum. We need to take a look. And I provided an overview of the opportunities and challenges, and also presented a set of solutions, how we are able to proceed here. So with this, let me thank first, these are all the organizations where my own work has benefited. We have been able to continue with all those MPI, AI, big data work. These are all my heroes over the last 24 years. As you can see, all these people have contributed here. But this is the bigger list of the icicle with all these 150 people. Okay? So I'm like I have condensed 25 years of my work into 59 minutes. Okay? So with that, let me conclude here. Thank you.